When we train a deep learning model, we're essentially trying to find the bottom of a very complex, high-dimensional valley, the loss landscape. This analogy works because, like a physical valley, we're seeking a low point. However, unlike a physical valley, we can't visualize these dimensions directly, and our descent isn't a continuous slide, but a series of calculated steps. It's not just about getting to any bottom, though.
Why isn't finding any minimum good enough? The goal is to minimize the error on our training data, right? What's the fundamental challenge we're overlooking?
That's a common initial thought. Historically, local minima were seen as a huge hurdle. This text points out, though, that for neural networks, local minima are no longer believed to be the primary problem.
If it's not local minima preventing us from getting good results, what is it? Is the landscape just too complex to navigate effectively, leading to suboptimal solutions?
It's about how we navigate it and how the model behaves beyond the training data. Even if local minima aren't the main issue, the book notes that continuation methods can still help with optimization.
What exactly are continuation methods in this context? That sounds like a strategy to smooth things out or make the problem easier to solve incrementally over time.
You're spot on. The text gives a great example. Curriculum learning can be interpreted as a continuation method. It's about structuring the learning process itself to make it easier.
Think of it like teaching a child basic arithmetic before moving to calculus. This parallel holds because both strategies introduce complexity incrementally. Where it differs, however, is that for a child, simple concepts involve cognitive development, while for a neural network, simple concepts might mean less diverse or less noisy data, or tasks with fewer classes. Curriculum learning mirrors this by planning a learning process to begin by learning simple concepts and gradually increasing complexity, smoothing the path.
This isn't just theory. Early work showed better results could be obtained by following a curriculum for large-scale neural language models. It's a proven way to simplify the optimization journey.
So, curriculum learning helps navigate complex landscapes. This suggests there's more to optimization than just finding any minimum. What kind of minimum should we be looking for?
That's exactly what this paper digs into. Imagine two valleys, both equally deep. One has steep, jagged walls, while the other is wide and gently sloping. Which one would you prefer to build a house in? This analogy helps us understand stability. A house in a gently sloping valley is more stable. In our context, stability translates to a model's performance being less sensitive to small changes in its learned parameters, making it more reliable when faced with slightly different unseen data. A house represents our model's final set of parameters.
Definitely the wide, gently sloping one. It feels more stable and resilient to small tremors. But how does that relate to a neural network's house, its learned parameters?
This paper explores the structure of these valleys or loss functions to find good minimizers of highly non-convex loss functions. They're not just looking for any minimum for training.
The key insight is that the shape of these minimizers, whether they are sharp or flat, has a profound effect of loss landscapes on generalization. A flat minimum is like our stable valley.
So a sharp minimum would be like that jagged valley where tiny parameter shifts make a big difference in loss. And a flat minimum is where parameters can change slightly without loss spiking dramatically.
Precisely. The authors visualize how network architecture affects the loss landscape, showing that some designs, like skip connections, naturally lead to flatter, easier to navigate landscapes for training. It turns out that training parameters produce minimizers that generalize better. It's not just about the model's architecture, but also how we train it, the batch size, learning rate, and optimizer choices.
I see. So if we only focus on getting the training loss as low as possible, we might end up in a sharp minimum that looks good on the training data, but performs poorly on new, unseen data.
Exactly. A sharp minimum means the model is highly sensitive to small perturbations. If the test data is slightly different from the training data, performance drops significantly, indicating poor generalization.
If flat minima generalize better, how can we explicitly encourage our optimization process to find them, instead of just hoping for the best with careful hyperparameter tuning?
This is where Sharpness-Aware Minimization, or SAM, comes in. It's an optimization technique that directly addresses the problem of finding flatter minima with better generalization.
The paper starts by asserting that training loss provides few guarantees on model generalization ability. This reiterates our earlier point. A low training loss isn't the entire story for a good model.
Before we dive into how SAM works, let's concretely define sharpness in this context. The paper states that for a given set of parameters W, its sharpness is defined as the largest increase in loss within a neighborhood of W, of radius P. So it's about how much the loss can increase if we perturb our parameters slightly within a certain boundary.
So a sharp minimum would be one where even a tiny wiggle in parameters causes a big jump in loss, meaning that largest increase is substantial. A flat minimum would have a much smaller or even negligible largest increase within that same neighborhood. So SAM aims to find a minimum that is not only low in loss, but also flat enough to generalize well, right? How does this technique actually do that mechanistically?
Instead of just minimizing the loss, SAM is designed for simultaneously minimizing loss value and loss sharpness. It's a dual objective that considers both how low and how stable the minimum is. Imagine you're searching for the lowest point in a valley. SAM doesn't just step to the lowest point, it takes a peek around that point. This peaking is like actively probing the immediate surroundings of a potential minimum. It's an analogy for how the algorithm mathematically evaluates the loss at slightly perturbed parameter values, not literally looking. It seeks parameters that lie in neighborhoods having uniformly low loss.
A neighborhood implies checking nearby points. So it's not just the current gradient, but also how much the loss changes if you wiggle the parameters a bit in any direction?
Precisely. This peeking around translates into a specific type of optimization, a min-max optimization problem on which gradient descent can be performed. It minimizes the worst-case loss in a small vicinity.
For each step, SAM first computes a small perturbation of the parameters that maximally increases the loss within a tiny radius. Then it takes a standard gradient step to minimize that perturbed loss.
To formalize that peaking and then minimizing process, SAM tackles a min-max problem. It first finds a perturbation, epsilon star, that maximizes the loss within a small sphere of radius rho around the current parameters W. Practically, this epsilon star is often approximated by taking a step in the direction of the gradient, scaled by rho and normalized by the gradient's L2 norm. So we approximate epsilon star as rho times the gradient with respect to W of L of W divided by the L2 norm of the gradient with respect to W. Once this worst-case perturbation, epsilon hat of W, is found, SAM then computes its gradient at that perturbed point. This means the SAM gradient is approximately gradient W
L of W plus epsilon hat of W. The optimizer then uses this gradient to update W, effectively minimizing the loss at the sharpest point in the neighborhood, pushing the model towards a flatter minimum. This ensures the model learns parameters that are robust not just at W, but also in its immediate surroundings.
That's clever. It's like it's actively trying to smooth out any sharp edges or steep inclines, forcing the optimizer towards truly flat regions, making the model more robust.
Exactly. This procedure, Sharpness-Aware Minimization, SAM, ensures that the chosen minimum is robust. It's not easily disturbed by small changes in data, which is key for real-world scenarios.
Now that we understand how SAM works at a high level, let's look at the concrete benefits it provides when applied to various deep learning tasks in practice.
The practical results of using SAM are quite compelling. The paper demonstrates that this explicit focus on flatness pays off where it matters most: improved generalization to new, unseen data.
They found that SAM improves model generalization across a variety of benchmark datasets like SciFAR 10, SciFAR 100, and ImageNet. This isn't just a theoretical improvement, but a tangible one.
So we're seeing tangible improvements in how models perform on data they've never seen before, simply by being smarter about how we find the minimum during training?
Absolutely. In some cases, SAM even achieved yielding novel state-of-the-art performance for several tasks. This shows that explicitly focusing on loss landscape geometry is a powerful lever for better models. Beyond just raw accuracy, a critical benefit is robustness. The authors found that SAM natively provides robustness to label noise, which is a huge deal for real-world datasets that often have imperfect annotations.
That's a fantastic bonus. If the model is less sensitive to small changes in its parameters, it makes sense that it would also be more forgiving of noisy labels in the training data.
Exactly. This explicitly addresses the pitfall identified. Optimizing only the training loss value can easily lead to suboptimal model quality. SAM provides a direct, effective solution to this common problem.
This all sounds incredibly powerful. Are there any downsides or situations where SAM might not be the best approach?
That's a crucial question. While SAM often improves generalization, it comes with a computational cost. Each optimization step requires calculating the loss and gradients twice, once for the perturbation and once for the actual update. This can make training significantly slower, especially for very large models or datasets. Also, tuning the radius of the perturbation, often called rho, introduces another hyperparameter that needs careful selection for optimal performance, and finding the right balance between sharpness and loss isn't always straightforward.